Hello, I'm David Valdés, and today I wanted to talk about Pythagorean Theorem applications. So let's take a quick look at the Pythagorean Theorem in general, and then we'll put some application to it. So the Pythagorean Theorem is often stated in terms of a right triangle here, where we have a side length of A, B, and C on each side. And even though the Pythagorean theorem is technically a statement about squares, we usually, again, apply it to the right triangle. Right has this little box in there. It means that one leg is perpendicular to the other leg. And the Pythagorean theorem looks like this. Here, I'll put it up here. A squared plus B squared equals C squared. There are lots of fun proofs to the Pythagorean theorem, but just to apply this to some of the things we do in algebra, let me go ahead and give you the distance formula using the Pythagorean theorem. So suppose we had a point here and some other point here. It doesn't really matter. And we're concerned about what is the distance, we'll call it d, between those 2 points. Now, oftentimes in algebra, we're dealing with a Cartesian coordinate system, or the xy graph. And so let me just sort of impose an xy graph here. Here's a y, here's an x. Now, how can I possibly find the distance between these 2 points using this xy graph and also using the Pythagorean theorem? Well, if I consider the distance between these 2 points as this long length c, then I can sort of make my own little right triangle. Okay, that's not really there in the first place. I'm just deciding to put it there. But really what I'm concerned about is this distance. Well, remember that each of these points in the Cartesian coordinate system has an x and a y. So this one, this point, corresponds to somewhere here on the x-axis, and we'll just call it generically x1. We'll also say that it corresponds to generically y1 on the y-axis. And we can play the same game with this other point. And I see that I didn't really draw my axes high enough to represent this well, so let me just give it a quick erase. Pull that down. OK, this is the y-axis. I'll do the same over here, just move it over a little bit. All right, there we go. OK. So this point, the second point, would then correspond to some x2, and up here correspond to some y2. The little subscripts just stand for the point. So point number 1, point number 2. Oh, there it is, point number 2. Now, if I'm thinking about my A, B, and C, this is where the A would go, this is where the B would go, and C I'm replacing by D for distance. But what are the A's and the B's? I don't really want A and B. I want it in terms of my X's and Y's. So A is the distance between x1 and x2. How can we get this distance between x1 and x2? The total distance from 0 to here is x2, yeah? The total distance from 0 to here is x1. Let me just sort of generically represent that like so. So how do I get the distance between these two guys? Well, I can take the total distance x2 and subtract x1. So this must be x2 minus x1. So essentially, that's what my A is. It's x2 minus x1. And we can play the same game with the y's and say that the distance in between here must be y2 minus y1. So B, this piece, is equal to y2 minus y1. So if I were to generically use the Pythagorean theorem and say, OK, a squared plus b squared equals, now I'm calling it d squared, I'm just going to replace my a with that distance that we just determined, which is x2 minus x1. I'm being careful to use a set of parentheses because I have a square on the outside of my a. And it doesn't just apply to this one or this one, it applies to the whole distance, okay, or difference here. So let me add the b, which we said was y2 minus y1, that whole thing squared. And of course, that's still equal to d squared. I could turn this around to have my distance on the left side. And here's the same equation. This one is actually very useful. You might want to hang on to this equation. It's not technically the distance, it's the distance squared, but this tends to be pretty practical when you're plugging numbers, into this, and then eventually solving for a distance by taking a square root at the very end of the things you do, instead of carrying this root symbol the whole way. Now, I'm getting ahead of myself. To get the distance by itself, since it's squared, we have to take a square root of that distance. Okay? So the square root of d squared, that gives me d all by itself, but I have to do it also to this side. And here's the rest of that equation. I'm going to point a couple things out here. One thing I should point out is, notice that when I did the square root, I didn't put a plus and a minus on this side. You really, that's the typical method in math. When you take a square root of both sides, you use a plus and a minus to account for the fact that you have both positive and negative solutions. However, with distance in particular, if we're restricting it to that, then we're going to say that distance has to be a positive value. So I don't need the plus and the minus. I'm just going to leave it as positive, which means I don't have to put a symbol in front of the square root. The other thing I should mention is that often mistakes are made when people take the square root of this plus the square root of this. But you can't exactly do that when there's a plus right here. You'll see that that would come out to something different. And actually, I encourage you to play with numbers and do that on your own. So for now, here's the simple formula that you see in the back of a lot of textbooks. The distance is equal to the root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And that's it. There's the distance formula. So in the next video, I'll do just a few examples of using the distance formula to determine the distance between 2 points.